In this video, we're going to demonstrate how we take the CAD that we've been working on for our tensile structure and then perform finite element analysis on it with a specified load that we've been designing to accommodate. So let's get back to the design we completed in the previous video. I haven't done anything to my part at this point. I believe it's the same one that we just completed from the previous video. And what we're going to do here is prepare it for finite element analysis. Now, we're going to be pulling this part apart, okay? And it's going to be a tensile load in the horizontal direction, the way we've got things drawn here. And what we would kind of like to do for the sake of simulation is have two faces, one on which we can provide constraints, make it like fixed so it doesn't move, and then the other side we're going to apply a force that's going to be pulling it toward the right side. I realize that my hands might be backwards because that's how I'm looking at the part, but it'll be flipped, I guess, when we do this. So let's go to it. We're going to go ahead, and again, we're going to be on the bottom face, okay, which we are. We're going to click on that surface, and now what we're going to do is create another sketch. So we come up here, and we once again see that we have the center point here, and we want to cut away. All right, we're gonna, this curved region is great, and we use it for laser engraving or cutting the samples that you're able to use and cut further. But for our finite element, it's kind of not necessary. So we're gonna cut it away. What actually happens is the grip will come and clamp down on this region, and then put the rest, the middle region, into tension when we pull it apart. So what are we going to do? We're going to come over to this rectangle feature right here, and we're just going to draw a rectangle like this, okay? That we make sure it goes outside the bounds. I'm going to draw another one over here that also goes outside the bounds. And then we're going to come to our nice horizontal constraint, or constraint horizontal distance tool over here. Click in the middle, and then click this left point here, and I'm just going to make it 40, like that. Okay, and then come over here in the middle again. That's good. And then click on that point, and again make it 40. Okay, I'm going to close the sketch. And you see it's not real precise, not real pretty. And we're going to do another pocket. So we remove that, and wow, now we've gotten rid of the ends. And this gives us nice surfaces to which we can apply constraints. Where are these surfaces? Well, if you come over to the upper right little cube and you click on this right one, what you'll see is that as I rotate back and forth, now I'm clicking on the left one, and I'll try to do a Control-Shift+, okay, that you can see that there's this surface that will be able to, not that one, not that one. I guess I better do a little more Control+, and I'm trying to make it so I don't have to do this, but we are going to, fine, I'm going to go to Tinkercad, sorry for those of you, okay, and I'm going to use my mouse. All right, this surface, that's what we're going to be highlighting in just a minute. Okay, so I'm going to come back out, move things back here, and I'm actually going to go ahead and move things like that. I'm using the middle button. I like the Tinkercad option because it allows you to do the 3D rotations on your mouse without having to push a key. I mean, you can do that for other things, but it does the rotations, and it does the zooming with the mouse wheel, and it does the panning like this too. All right. Enough of that. We're going to hit OK here because we like what we've got. And now we're going to open up another workbench. We've been using the part design workbench. We're going to go to the FEM, finite element method. Okay, and often you don't do finite element analysis or use the finite element method until you get into more advanced courses. But this package is pretty straightforward and simple, and by following these steps, I think you'll get to see the power of this technique. Even though this is not commercial software and it's still maybe not as friendly as some of the packages that are out there, but it is available for all of us to use. So that makes it easy for everyone to download it, which you've already done. Okay, so we now are in the finite element method workbench, and you look over here in our model and nothing's changed. Nothing's changed yet until we click analysis. So we're going to hit this analysis container. Now it's added this. The order is not necessarily fixed, but we'll kind of move from left to right on these tools up here. So we did the analysis container. We've got one analysis container. This, for better or worse, is how you define the material. It's just a sphere. And we're going to go down to using wood generic. It turns out for our problem, it's not particularly important that we have the appropriate density and Young's modulus and Poisson's ratio, but that's what, well, I guess I had to move this. That's what are getting defined here, okay, with this material. We click OK, and if you left click over here, you'll see that now there's been a material solid added. Okay, again, kind of moving from left to right. We're not going to do every one of these. We're not doing material for a fluid. This is not a fluid problem. We're not reinforcing. We're not doing beam cross section, at least not how it's defined here. We're moving over. Okay, now we can do a constraint fixed. Okay, we do want to constrain one side of the beam. So we click here, and it's asking us to add a face. So we click on that, and remember we need to add this. So in order to do this right, we want to tilt up on this cube. There we go. Tilt like this. And it's okay. Like I could just be looking directly at it the way I've done it. Control Shift plus to make it nice and big, and then I click on it. It's a little bit yellow, and boom. Now it's in there. I guess it's face 19, pocket 3, face 19. And then I can do Control minus. We come out, and we can do this left thing right here, and you can kind of see that if we look at it maybe a little bit more, Control minus. Okay, it's essentially fixing the left side of the structure. We hit OK, and we move on. So we were here. Now we're going to skip a lot of this stuff. Bing, 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 bing. Okay, we were going to add a force. Okay, so we click on this, and we're going to click on Add over here on the left, and then we're going to click on this little arrow to kind of turn things. Right, you see that? And I'm going to do a Control Control Shift plus, or Control Shift equals, which gives us plus, so you can get it nice and big. I highlight it, click it. I guess it's pocket 3, face 9. Great. And then I hit OK. And I can go back to the cube and hit the right one. And it's really huge and messy. So I'm going to do Control minus. And you can kind of see it's tilted. And we got these arrows coming this direction like that. I'm going to hit another minus. Okay. And then I'll do Control or another right. And I'll do another Control minus, and voila, that's what we've got. Now, I've got a constraint force. What I really should do, though, is specify the force that I thought my material was going to break at. Okay, and it's been a while. Okay, but my breaking force was 1.5, my safety factor, times my design force. So I had a design force of 50 newtons and a safety factor of 1.5, which means that my breaking force was 75 newtons. What we're trying to do is simulate this material under appropriate loading to then have a stress within it that matches the ultimate tensile strength of the material, because that's when we think, or that's the stress at which we think the material is going to fail. So I'm going to go back into my constraint force, and the load here, it says 1.00 newtons. I'm going to put that as 75 newtons because that's the force I think I'm going to be having failure. I hit OK. Okay, so now I've done the constraint force, or rather that force, and I go to the right, and actually what I need next is this net gen. I need this FEM mesh from shape by NetGen, okay, right here, but it's grayed out. A little counterintuitive maybe, but I go back up and I click the body, and what do you know? Now it's no longer grayed out, but it's yellow and red, right? So this is going to allow us to add a mesh to the body, so it wanted me to select the body. So I click it, and now I've got some options. The max size, right? So if you make it a large max size, that's going to make it so that a mesh. So a mesh is what it sounds like. It's going to kind of take this object and discretize it and make lots of little things, and it's going to be like a net, a web. Okay, and think Spider-Man or something, just putting a web, but it fills up this whole thing, and it's called finite element because it takes something that theoretically has infinitesimally small components to it, and says we're going to approximate the geometry with a bunch of elements. Okay, so here, if you want to do for your max size, you can put 1, and then we'll say fine for the fineness. Okay, so 1 and fine, and then we'll hit OK. All right, and there you go. This is a mesh. It's a 3-dimensional mesh. Okay, through the thickness as well, and it's a little bit of an art here, but this is pretty well refined. Remember I mentioned that these little like odd corners here, because of these sharp corners, or they're not super sharp, but because of these little dips in the sides, to approximate that geometry has to put lots of meshes, so it kind of refines the mesh around those points. Okay, it won't be a big deal, but it's just so you understand why it's doing what it's doing. At this point, we can go back to our analysis container, and we see we've got things going on. We've got mesh, we've got material, and then we're moving again from left to right, and those things are no longer highlighted. We're going to click solver, and then that is going to put a solver into our analysis container. This is using CalculiX. It's an open source finite element library. We can then, in mine, yours may be a little bit different, okay? But after you click solver, you go over here. Oh, and it's not highlighted because, well, I guess I have to click on solver. So now I click on solver over here, solver CCX. And then I'm going to click on this one that says run solver calculations. Okay, it's this yellow one with a bunch of stuff around it. So I click on it, and then my computer is going to do some thinking. It is solving for displacements, and it's solving for loads on those individual elements. Okay, it's now done solving and doing this to then calculate out what the stresses are. Okay, so now if we go here and we click on the CCX, or if we double click on the CCX results like this, okay, there are kind of a couple of different things I'll show you here. So first, this is double clicking on this, so I'll just close it again. I'll show you. Double click here on CCX results, and this can get a little bit messy. All right, so just stay in there. And you're like, well, it's all one color. Well, why is it all one color? It's all one color because its result type is none. Okay, and there are multiple different items here that you can be thinking about using. When you take mechanics of materials, I'll explain, or will explain, what a lot of these are. But for now, let's just use von Mises. All right. And von Mises stress is essentially giving you an equivalent to what you would be thinking would be breaking for tensile test. Okay, it's actually using maximum distortion energy theory. Anyway, we don't need to get into that now, but look at this. Look at this. This is very exciting. When I clicked on von Mises, it told me that the max was 33.56 megapascals. Now, one thing to note about finite element is that it's not like your nice analytical solution, which you can just divide some numbers and it's going to be really accurate to who knows how many decimal places, right? This is using a bunch of elements and then solving for the loads and the displacements on these elements to come with an approximate solution. So what did we say? Okay, what did we say the ultimate tensile strength of this material was, or that we were designing for? We said it was 33 megapascals. The maximum load is 33.56, 33.6 megapascals according to this. This is very exciting. And you can't really see this legend. I'm not quite sure how to make it look better. I looked up online a little bit. It has to do with some VTK, something like blah, 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 blah. But and this is where it's like, okay, if you're using another commercial software, there's a little bit better user interface and a little bit better graphics. But this is open source. It's incredible, and you can export this result to something like ParaView and really do some amazing visualizations. But just right here, this red is the max, and look, it's max in the middle. Okay, that's super exciting that the max is what we designed for 75 newtons. We wanted to have our maximum stress be the ultimate tensile strength. If we click on this histogram, this is kind of fun too. It's just taking all the nodes in. The nodes are all the corner points, okay, of these elements, and it's telling us, okay, this is what the stresses are in a histogram. So again, somewhere around, well, this is like 33.56, so we have a few nodes, maybe like 200 of them, which it's not insignificant number that are experiencing this maximum stress. And what we really want you to do at this point is to take a screenshot, okay, of this result showing the max value over here, okay, and Windows, it's not that hard to do it. You hit Windows Shift S and then take this screenshot and bring it into whatever tool you have and save it. And where am I going to save it? I guess I'll save it. I have screenshots, but I'm already been sloppy enough, so I'll just save it to the desktop again. And this is what you're going to want to upload, okay, to at least one member of your team should upload it to the Excel spreadsheet that you have access to for the lab, okay? Now, you can do some other cool things. You're done, but if you want to keep watching, I'll show you some other cool things that FreeCAD allows you to do. Here, if we click on this pipeline CCX results, so I move down one and I move over here, I can do what's called a line clip filter, and I click on that, and then I can specify X, Y, Z points for a line, for 2 points on a line. So if I do this, I'll say, oh, let's go minus 40 to the left. Okay, remember I did some clipping at 40. And I'll go to 40 to the right, and I'll click this 0Z. So now I'm just on the 0Z. This is only 0.3 millimeters thick, and it's coming from the bottom up. So I guess, well, let's see, Aaron. If we do 0.15, that would be giving us right down the middle of the part. Okay, I mean, I've done 0 before, but let's try it. We'll see what happens. And then I'm going to do, for field, I'm going to go ahead and I'm going to use von Mises again. You could do you can do a bunch of different things here, but let's just, since we've been using von Mises, we'll do create plot. Okay, and look at this. Look at this. So what is this doing? This is telling us, as we go from the left to the right. Okay, so remember this is minus 40 to plus 40, so that's a length of 80 um, millimeters, all right, which is the entire length of the part. This plots along a line, and it'll be a little bit more obvious in a second, what the von Mises stress is, okay? And look, it maxes right at the middle. 40 would be right at the center. This is super exciting, okay? And maybe it's a little bit different here. It's a little bit under 33 megapascals, okay? It's like 32, I don't know, maybe 32.4 or something megapascals. That's okay again, right? We're trying to get it to be about the 33 megapascals for the ultimate tensile strength that we've been designing for. So this is another cool chart that I can maybe save again to my desktop. The von Mises stress across it. Okay, maybe you want it for your good to know file. And so I've got this, and I can hit OK. Okay, and you can kind of see if I look, I've got this data along the line. All right, and oh, there's another thing I can do right over here for pipeline CCX results. Whoops. I can do a wireframe, okay? And if I do wireframe for it, so what did I do? I double clicked on this again. Before it was on maybe what was it on? Was it on outline, I think? I'm not quite sure, but now I'm doing wireframe like this, and you can kind of see if you look carefully. Do like a Control Shift plus. Oh, it's not actually letting me do it. It's not letting me zoom in. Oh, that's sad. Okay. I don't know why it's not letting me zoom in. Maybe now. Yeah, Control Shift plus. And you can kind of see that that line that we created, it's going right down the middle, and it's red here. Okay, it's hard to see probably on the YouTube video, but if you do it yourself, you'll see that there's that line that we can zoom in on and zoom out on, and that's the data along line that we created here. All right. If you want, you can take another screenshot of this. I think this is kind of cool, but you don't have to, and I'm not going to right now. Well, this concludes our tutorial on how to simulate a cross section, and I hope you find it interesting. I think it's wonderful that FreeCAD provides these powerful tools. Thank you.